If I took a couple of drops of gasoline and lit it, we'd get a little bit of flame and generate a little bit of heat. Now, if I took a gallon of gasoline and lit it, we'd get a lot bigger fire and generate a lot more heat. The amount of heat that is measured in a chemical process depends upon the scale of that reaction. In the words of chemistry, it depends upon the number of moles of reactant we start with. We are often presented with what is called a thermochemical equation. This is simply a balanced chemical equation with a piece of thermodynamic data. For example, here is a balanced equation for combining 1 mole of hydronium ions with 1 mole of hydroxide ions to form 2 moles of water. The thermochemical equation tells us that delta H for this process is negative 50 kilojoules. That number is specifically for the number of moles shown in the equation, in this case forming 2 moles of water, from 1 mole each of hydronium and hydroxide. It is also specifically for the direction shown in the equation, the formation of water as a product. The actual value of delta H will depend on the scale and direction of the reaction in question. For example, what about running the reaction in the reverse direction? Let's take the thermochemical equation given on the last page and ask, what is the value of delta H for this process? First of all, we notice that water is the reactant instead of the product, going on to form hydronium and hydroxide. So the reaction is being run in the reverse direction, and the value of delta H will have the opposite sign. We also notice that the number of moles is the same, 2 moles of water in each reaction, so the magnitude of delta H will be the same. The value of delta H for this reaction would be positive 50 kilojoules. We can also find delta H if the reaction is run on a different scale. Again, we have our given reaction. Now we want to find delta H for this reaction. First, we notice that water is the product in both reactions. So they are in the same direction. They will have the same sign. If we look at the scale of the second reaction, we see that 4 moles of water in the second reaction are formed instead of 2. Since there are 2 times the number of moles, the value will be 2 times the magnitude. For this reaction, delta H will be negative 100 kilojoules. With 2 small modifications, we can use this concept for any size sample. For example, what is delta H when 1 gram of water is formed from hydronium and hydroxide? First, we need to know how many moles are in the reaction. We can use the molar mass of water to find that 0.0555 moles of water are formed when 1 gram is formed. Second, we can turn our thermochemical equation into a conversion factor. Since negative 50 kilojoules is for the formation of 2 moles, or it is per 2 moles, we can take our number of moles and multiply it by the conversion factor negative 50 kilojoules over 2 moles, which results in a value of delta H of negative 1.4 kilojoules. Again, we need to know that the number in the thermochemical equation is for forming 2 moles of water. So if we're only forming 0.0555 moles, the enthalpy change should be much smaller.